Alright, so in this video today we're going to be talking about what it means to solve for a volume integral in spherical coordinates. So before I really get into illustrating that point, I just want to quickly take a look at what spherical coordinates are. And so one thing that you're probably used to is rectangular coordinates. And so we specify these by drawing these little dotted lines to each axis, as I'm doing right now. And if we do that, we'll have these little intersections with the axis, and that gives us an x and a y and a z, which I've called x1, y1, z1 in this case. But of course that's not the only way we can specify a point's location in space. So the other way to do this is going to involve three different variables. So instead of having x, y, and z, we're going to have r, phi, and theta. So in no particular order, I'm going to draw these out now. So right here, if we extend down to the xy plane and then find our angle with the x-axis, there's our phi. And the next one I'll draw is similar, it's theta, and that is the angle between the z-axis and the vector that goes from the origin to our point P. And then the length of that vector, I'm just going to call r. You might see it called other things, but in this case, I think r is a good name for it because it is going to end up being the radius of the sphere whose volume we solve for. So we have r, phi, and theta to specify our point. Alright, so now that we have our variables, let's talk about going from rectangular to spherical in terms of our integral that we're going to end up taking. So if I want dx and dy and dz to become dr, d phi, and d theta, these things aren't just equal to each other. I need to actually have a little bit of a correction factor between them. So what exactly that means has to do with some linear algebra, and it's not something I necessarily want to spend time in this video explaining, although we could do a different video to talk about what that means. But our factor is going to be r squared sine phi. So there it is, r squared sine phi. And then we'll have our dr, d phi, d theta. So if I multiply dx, dy, dz, I get r squared sine phi, dr, d phi, d theta. And so let's just take that for granted for the time being and see if it's actually true. So when we go to integrate a volume, you've probably seen it before when people integrate dx, dy, and dz. So now that we've found our conversion factor, and we now know what dx, dy, and dz are equal to in spherical coordinates, it's as easy as just applying our triple integral to this instance. So that's what it looks like. And something I want to point out is that r squared sine phi dr, d phi, d theta is a bunch of separate things multiplied together, and none of each of those things depends on any of the other things. So r squared doesn't depend on theta or phi, and sine phi doesn't depend on r or theta, which means I can do something a little unique in this case. I can actually split the integral apart. So in this video, that's exactly what we're going to do. We're going to split our integral into three different integrals that don't depend on each other and multiply the results. Of course, that's not always true, but because these are all separate things being multiplied together, we can perform that action. So let's start with the r integral. So we're going to integrate our r variable from 0 to r. And of course, the only thing that uses r in that big integral that we just wrote is r squared. So we'll integrate r squared from 0 to r. And I'm going to solve this out for you right now, but it's very easy to find that antiderivative. We can just use the power rule. And what we end up with is big R cubed over 3. So big R is going to be the length of the vector that extends from the origin to whatever location we're talking about. So now I'm going to actually show you what that looks like visually. So I'm going to draw a line, and my line is going to go from the origin, and it's going to go out some distance big R, which I've named radius. So there it is. It's as simple as that, just extending a line from the origin to some point. Now I'm going to do phi. So the only thing that depends on phi in that big integral we wrote is the sine phi term. So we'll integrate sine phi from 0 to pi. So 0 to pi is actually going to be the angle that we're sweeping over, and you're going to see exactly what that looks like in a moment. But for now, trust me that we're going from 0 to pi. The antiderivative is negative cosine phi from 0 to pi. So we have to be careful with our signs here. This is a negative cosine phi. So cosine of pi is negative 1, but that's negative. So we have negative negative 1 minus negative cosine 0, which is also negative 1. This is going to give us positive 1 plus positive 1 equals positive 2. So what does that sweep actually look like? Why are we sweeping from 0 to pi? Well, you're going to see it right now. I'm going to take an arc, and I'm going to start at my line and go out to that point that I found. And then I'm going to perform the sweep. So this is what the integral actually looks like. I'm sweeping from 0 degrees to 180 degrees, which is pi in radians, from 0 to pi. And then I'm going to close this up so that we have a nice solid, which will set us up for our next step, because we've got one more integral to perform, and it's our easiest one. So that's what we have now. Now we have a 2D image. So what I'm about to do is take my theta integral, and if you remember, nothing depended on theta, so it's actually just the integral of d theta. And that's very easy. The integral of d theta is just theta. And this time we're going from 0 to 2 pi. So again, you're going to see exactly why that is in a moment. But here I go, and I'm going to do 2 pi minus 0 gives me 2 pi. So, like I said, that's the easiest integral we have. But it's also a very important integral, as you're about to see, because when I take the thing that we just made, and actually the software beats me to the punchline here, when I sweep our semicircle that we made earlier, when I sweep it 2 pi radians, or 360 degrees, around itself, actually closes up a very nice sphere. So there is our solid. And in other words, there's our volume. So I'm going to do it again because I really want to make this clear. When we sweep our two-dimensional semicircle, we end up with a full sphere. Now, if I only sweeped from 0 to pi, we'd end up with a hemisphere, which is just the top half of that sphere. But if we go from 0 to 2 pi, we get the entire sphere. So now we can finally solve for the volume of the solid. So I'm going to rewrite our answers again. We have big R cubed over 3, and that's going to be multiplied with just 2, and those are going to be multiplied with 2 pi. So if I perform this multiplication, what we're going to see is something very familiar. 4 times pi times r cubed all over 3. And that is the famous volume of the sphere integral that we learned many years before we took calculus. And now we're going to check if it works. So, does this integral give us a realistic answer? So I made my r 1 inch to make it easy. So let's say r is 1 inch. That means r cubed is going to be 1 cubic inch, which means if I put that into my formula that I just found, here we have the volume is equal to 4 pi thirds inches cubed. So 4 pi over 3 inches cubed. And if you put that into a calculator, you're going to get about 4.189 cubic inches. So here's where we're going to actually finally check our formula. So in less than a page, we actually derived the formula for the volume of the sphere. So let's go ahead and check it and make sure it's good. I'm going to select our sphere and check the properties, and Fusion 360 is nice enough to actually tell us that the volume is 4.189 right there. So it turns out our formula does work, and we have found for the volume of a spherical region. Now, doing this using a rectangular coordinate system, dx, dy, dz, would have been really hard because our volume is changing over each of those axes. But in this case, it's a piece of cake. So it turns out spherical coordinates tend to be extremely useful things to keep in mind. So right now, you're just going to see me draw this out again because I want to make it very clear exactly what these things look like. So one more time, this time unedited. I'm sweeping my arc, so I've done my first integral, There was my second integral. I just finished it. Now I'm turning this into a 2D image, right? And finally, I'm going to do my revolution. Here's my third integral. Remember, this is the integral that goes from 0 to 2 pi. All 360 degrees. Now, one thing I want to say is that we don't sweep phi all the way to 2 pi. Because if we did that, we'd be counting a region more than once, right? So if I actually extended our phi integral out from 0 to 2 pi, and then did the theta integral from 0 to 2 pi, we'd double count a certain region, and that would give us an inaccurate volume. So we're going to be careful with our bounds, careful with our signs, and we'll come out with the right answer. So that's it for this episode. Thank you for watching. Leave your questions in the comments.